And I'm He Qinglin from Shanghai University, and I'm very happy to attend this conference. And I'm the speaker of this article, Unsupervised Blind Image Quality Assessment based on multi-feature fusion. And I will introduce it in 5 parts. It includes introduction, framework, feature extraction and fusion, experiments, and conclusion. So I'll introduce it with the rapid development of multimedia. The quality of images not only affects the visual experience of observers, but also has an impact on image processing algorithms. In addition, in the image process of images, such as acquisition, compression, transmission, and display, various distortions would be introduced. The quality of image is influenced. That's why image quality assessment is so important. Image quality assessment is also called IQA, can also not only ensure the image quality, but help algorithms to improve the image quality. Here are 3 main contributions. First, we propose a multi-feature fusion framework for unsupervised blind image quality assessment. Second, we select 4 features and fuse them for the MVG model fitting. And third, experiments show that the proposed unsupervised method achieves better performance with lower computational complexity on different databases. I'll introduce the IQA classification. There are 2 primary categories of IQA, namely the subjective evaluation and the objective evaluation. For the subjective evaluation, scores of different people on the same picture are needed, and that is costly and time-consuming. In general, the objective image quality assessment can be classified into 3 types, which are full reference, reduced reference, and no reference, which is also called a blind IQA. Full reference IQA methods need the original image and its distorted version to fit the model. And the reduced reference image quality assessment methods need features of the original image. No reference image quality assessment only needs distorted images to predict scores. In full reference and reduced reference IQA methods, the need for the original image as a reference limits the practical use. On the contrary, the BIQA methods do not have such strict requirements for model fitting and evaluation. What's more, BIQA can be divided into supervised and unsupervised models. Supervised approaches usually utilize subjective scores as the ground truth to train the model. Unlike supervised approaches, unsupervised approaches can reveal better generalization capability with fewer manually calibration data. How to measure image quality with lower computational complexity and better generalization performance has been a hotspot. The score of each image is the main evaluation criteria. On the other hand, models without human involvement are easy to use on large-scale databases. The goal of image quality assessment is to fit the objective score as close as possible to the subjective score, which means we could extract well-chosen features to imitate human behavior for more precise scores. And this is the framework. We fuse structure features and natural scene statistics, NSS features, and MVG model means multivariate Gaussian model. Training and testing share the similar progress. We calculate KLT kernel in the training process with high contrast image patches. In the test part, we use all image patches and use the saved KLT kernel to extract the feature. We fit the MVG model with the feature matrix of pristine images as the benchmark. The difference between the benchmark model and the MVG model of the distorted image is taken as the objective score. To form the feature matrix, we extract structure features and SS features from each non-overlapping patch of the image, which contains phase congruency feature like PC feature, gradient feature, mean subtracted and contrast normalized MSCN feature, and Karhunen-Loéve transform feature, and we call it KLT feature. PC feature calculates the maximum moment of phase congruency covariance, which is used as an indicator of edge strength. Images with different distortion degree have different PC coefficients. You can see in the picture on it, like image A and C are pictures without distortion and Gaussian blur distortion, and the PC feature is quite different here. Here comes how to calculate PC feature. The responses of even and odd symmetric filters at position P of 2D signal S. We write it as En theta f and On theta f, where n refers to scale and theta f refers to direction. And where is the big F? It means the filter directions. And after that, we need the A and H, which A means local amplitude, and H means the local energy function. And epsilon is a small positive constant, and we use this equation to calculate PC. Besides, we convert the color from RGB to O space, use this matrix, and in O space, the performance of PC feature is much better. And we use PC to calculate to fit the Weibull distribution and use lambda and Q as the feature of the image. And here comes to the gradient feature. The gradient is an indispensable IQA index that represents the contrast and luminance information of an image. We use filters DH and DV, which means horizontal and vertical, to calculate the gradient. Same like the PC, it's not so easy to use GH and GV directly, so we use zero mean general Gaussian distribution to fit these results, and we get alpha and theta square as the feature. Here comes the NSS feature. MSCN feature is very important and widely used, and the calculation is here, where mu means the mean value and the theta means the standard deviation. We use the original image minus mean value and divide standard deviation plus 1, which means which protect it from a denominator in 0. And besides, we calculate the adjacent MSCN coefficients along with 4 directions: horizontal, vertical, mean, diagonal, and subdiagonal. After that, we found that the adjacent MSCN coefficients fit a symmetric general Gaussian distribution better. And for the 3 primary parameters in AGGD, we use gamma, beta left, and beta right. Besides, the relationship between beta left and beta right is also important, so we use eta to represent, and we choose GGD to fit MSCN coefficients and AGGD to fit adjacent MSCN coefficients. Here comes the Karhunen-Loéve transform called KLT feature. KLT is a data-driven feature extractor to extract features. First, we calculate the covariance matrix. C is covariance matrix, and we divide M into non-overlapped patches, where M is reused in MSCN feature, with size K product K to collect vectorized patch RU, and M is the average vector of each vectorized patch. Then we calculate the KLT kernel. We calculate the standard deviation of each row of C and take the corresponding row of the matrix whose standard deviation is greater than 0 to calculate the covariance matrix as KLT kernel. We write it as K, and we use image product K as, and we fit the P with AGD, and same like the gradient feature. It also had and the kernel set is set to 4. Here is a demo of image patch selection, and we use 2 scales of image patches, the original scale and downsample to scale. Like the height and the width are half of the original ones. Besides, patch size are 96 plus 96 and 48, product 48. And the second, we select high contrast patches for model training, which is high contrast, like this. You can see the flower and the butterfly are high contrast patches, while the background green is not high contrast patches, and we choose high contrast patches for training, and also for KLT kernel training. And last, all image patches are used for testing. For the MVG training, we use features from pristine images to get nu and sigma, where nu means mean value and sigma means covariance matrix. And we compare the difference of them, where mu1 and mu2 refers to the original parameters and the test parameters from the model, and Q as the quality. Here comes the experiments. Is a summary of commonly used IQA databases. First, for the pristine images, it's come from the NIQE article, and it has 125 images without distortion, and we use them to train MVG model and KLT kernel. Here comes the four 6 commonly used IQA databases, and the former 4 has distortion types with reference images, while the Live C and CID 2013 has no reference image and has real-world distortion. For the evaluation matrix, we use SROCC, PLCC. These two are calculate subjective score, the relationship between subjective score and objective score, and the value between -1 and 1. The absolute value, the bigger the results are better. And RMSE, root mean squared error, the smaller, the better. And the performance of unsupervised BIQA models on lab, which contains SROCC, PLCC, and RMSE. The proposed method reaches the best result of 3 criteria compared with LPSI, NIQE, IL-NIQE, SMP-NIQE, and our results are in red. This table shows the SROCC of the proposed method, as well as other BIQA methods. WA refers to the weighted average performance over 5 databases, and the weights are the number of images selected in each databases. And the first 3 methods are supervised BIQA methods, and the rest 5 are unsupervised BIQA method. For fair comparison, all the supervised BIQA models are trained on live database, and that's why live doesn't appear here. The best performance of supervised and unsupervised models are highlighted in red. The generalization of rank IQA is pretty good among supervised models, while the weighted average performance of the proposed method is the highest among unsupervised models, even higher than rank IQA. To show the generalization on distortion types, we test the model methods on TID 2013 database, which has 24 types of distortion. The best results of each type are highlighted in red. Average here means refers to the average score over the 24 distortions. Distortion types vary in the TID 2013 database, so reaching the highest score on each type of distortion is a great challenge for models. LPSI, NIQE, SMP-NIQE, and the proposed method all have 6 results in red. Among them, the proposed method has the highest average score at 0.6. Besides, the results of the proposed method are competitive on TID 2013 for both common and uncommon distortion types. To verify the statistical significance of the results, we apply t-test on the prediction residues of different objective methods. 1, 0, and -1 indicate that the proposed method is statistically superior, comparative, or inferior to the competing method on each database with 95% confidence. The unsupervised method is a little inadequate compared with supervised ones. The proposed method is no worse than other unsupervised models. The proposed method has comparable performance with NIQE and SMP-NIQE, However, it is better than LNIQE and LPSI on more than half of the databases. To demonstrate the effectiveness of structure and NSS features, we report the ablation test and on 6 databases. And the combination of these two types of features can significantly improve the performance. Both of these features are indispensable. And here, all images, and here the average running time of different unsupervised BIQA methods on live. All images in the live database are utilized for the running time test. The generalization performance is good for LLNIQE, but it has higher computational complexity, like 5.69 seconds. And the average running time of LPSI is very short, like 0.02, but the accuracy and the generalization ability is limited. The proposed method has the highest results of 5 databases on a weighted average. The generalization performance and running time are competitive. In conclusion, in this paper, we propose an unsupervised BIQA method based on multi-feature fusion using structure features and NSS features and get better results. In the future, we can extend our work to uncommon distortion types. Thank you for watching.